Hi everyone, we've just finished our discussion on chemical reactions and their evidences. So right now, let us move into discussing the types of chemical reactions. So in this lecture, we will be distinguishing the types of chemical reactions and predicting the products of chemical reactions. So there are five main types, so synthesis or combination, that means putting together; analysis or decomposition, which means breaking apart; number three is single displacement or replacement. Four is double displacement or replacement. And five is combustion reactions. So we can actually determine the type of chemical reactions by just looking at how the atoms are being rearranged into forming new products. So for example, here in synthesis or combination reactions, uh, things or atoms are put together. So for example, the reaction between carbon and oxygen gas. So carbon reacts with the oxygen molecule to form carbon dioxide. So the general term for synthesis reaction is A plus B is equal to AB, or A plus B produces AB. That means the atoms are just stuck together, okay? So new bonds are formed between all the atoms in the reactants. Another example is that of potassium and chlorine. So in here we have a dramatic chemical change going on such that it will give us uh, white crystalline solid. Okay, so in here potassium metal, as shown, will react with chlorine gas, the yellow gas here, to produce this white substance, which is potassium chloride. And you see that the equation is also balanced to follow the conservation of mass, the law of conservation of mass. We have a few more examples in here. So Na plus Cl, Mg plus F2, Al plus F2. So in terms of the ions, what actually happens here is that uh, aluminum wants to be stable, so it gets rid of its 3 electrons. So that's why it has plus 3. And then for each fluorine atom here, it also wants to gain one more electron to become stable. So that's why the charge is F minus. If you remember in ionic bonding, what happens between these two ions is we just crisscross and disregard the signs, such that we will end up with AlF3. Alright, AlF3. So the same principle goes with the reaction between sodium and the chlorine gas. So in here, we end up with NaCl, since the ions that are involved is Na plus and Cl minus. So crisscross, disregard the sign, you get NaCl solid. The same thing in Mg. Mg here, plus 2, okay, it's found at group number 2, A in the periodic table. The charge of fluorine is minus 1. And therefore, if we crisscross, disregard the sign, we get MgF2. And we mentioned already AlF3. So these are examples of synthesis reactions or combination reactions. You can go as many atoms as you want here as long as the bonds will hold. All right. Now, in terms of the number of atoms in balancing chemical equations to follow the law of conservation of mass, then that means the number of atoms in the reactants must be equal to the number of atoms in the products. So that is why we have to place the coefficients. Since there are two chlorine atoms in here, then one chlorine atom in NaCl, we must place the coefficient 2 such that we will have 2 atoms of Cl, and therefore sodium also follows. Alright, so your balance equation for the reaction between sodium and the chlorine gas is 2Na plus Cl2 will produce 2NaCl. Alright, the same thing with the other equation. So in here, the equation between magnesium and fluorine gas is already balanced because they have the same number of Mg atoms, the same number of F atoms. In the third example, we have AlF2. So in order to make them equal, so we have to place the coefficient 3 okay, which is our greatest common factor, so that we can get six fluorine atoms. And in doing so, since there are six fluorine atoms here, we are going to place 2 as our coefficient for the whole compound AlF3, and then 2Al also in the reactant side, so that they will be equal. Alright, so don't worry, there will be another video showing a lot more of examples in balancing chemical equations. So that is just a preview in a way. The second type of a chemical reaction is decomposition or analysis reaction. So an example is the electrolysis of water. When you say something decomposes, you have to break it down into its component parts. So for example, here is a water molecule. In electrolysis, you actually run electricity through the molecules such that their bonds will be broken. Okay, and then you end up with H atoms and O atoms. So what happens here is, in the general form, this is the opposite of synthesis. So there you have a larger molecule being broken down into smaller ones. So that's AB will give you A plus B. So you can use any agent of decomposition here, for example, heat, or you can have acids or electricity. All right, and so what happens is the result will be H2 and O2 gas, okay, not the individual atoms only. So water, once you run it with electricity, will produce H2 gas and O2 gas. And you might have heard of hydrogen fuels, okay, so this one can be used as a fuel. Another example of a decomposition reaction is the decomposition of mercury 2 oxide. Okay, so if you add heat to it, you will end up with the silver element here, or silver colored element here, which is practically your mercury. And then you have also your oxygen gases. So if you remember, hopefully you had it in junior high, wherein there is a burning splint, and then once the splint is put out and then you place it in this test tube, because there is still oxygen, then the splint reignites or restarts its burning. Okay, so that's mercury oxide decomposition. So here are a few more examples. The decomposition of magnesium oxide and GO2, calcium carbonate, and then hydrogen peroxide or agua oxinada. So once you place it on a wound, it readily decomposes into water and oxygen gas. That's why you see it bubbles. You see some bubbles. All right, agua oxinada. A single displacement, okay, for example, the reaction of zinc and copper 2 chloride. So in here we have a free atom. It's usually a metal because metals can exist as monoatoms or monoatomic species. All right, and then in here we have a compound of copper and chlorine. So what happens in a single displacement is that zinc will be able to displace, okay, or to substitute the element or the metal found in the compound. Okay, so ZnCl2 plus Cu. So there is a substitution going on. So in here we have AB plus C. So what happens is one species, the free species, will be combining now to form a compound with the previous atoms present in the previous compound. Okay. This is also an example of a redox reaction, but we'll go to redox reactions in a few more lessons. So another example is the reaction between lithium and water. So in here, lithium displaces one hydrogen atom such that you will have LiOH. You take note that water can also be represented as H, O, and then H, right? So what happens here is lithium, because it's very reactive, is able to displace one hydrogen atom such that you will end up with Li, okay, LiOH. but this time the bond is ionic. Okay, this becomes this becomes your hydroxide ion. The OH becomes OH minus. Okay, so this is a polyatomic anion. Once it reacts with Li, you get LiOH. Okay, crisscross, disregard the sign. Another product is hydrogen gas, which accounts for the bubbles. So, how do we know that a certain free element will be able to displace another in a compound? So, we usually look at the activity series, okay, which is used to predict whether a particular element or a metal will displace another element in a compound. So, in here we have the listing of the elements according to their activity. Okay, so from the left are the most reactive, and to the right are the least reactive. And you see here that gold is one of the least reactive metals. Okay, that's why gold is mostly valued because it doesn't get oxidized. It seldom reacts. Okay, unless you have a unless you have a combination of certain acids which we call aqua regia. That's the time gold will be decomposed. But in here, okay, we look at the arrangement of the activity of the metals in displacing each other out. In the second row, we also have the activity series of the nonmetals, saying that fluorine is the most reactive, so meaning it has the most power to displace another nonmetal. And bromine has more or less approximately the same reactivity with oxygen. Okay, so in terms of the metals, lithium is listed as the most reactive, and uh, followed by rubidium, potassium, cesium, barium, and so on. So the keynote here is the if you choose one element, for example, Na, so all the elements before Na will be able to displace it. Okay, so if you make this a reference point, for example, NaCl, and you ask whether there is a reaction that can happen between a barium atom and NaCl. Okay, so just take note that in the activity series, all the preceding atoms or the preceding elements for a certain element X can displace that particular element. So since barium is more reactive than sodium, therefore barium will be able to displace sodium, so that you will end up with Ba, and then since the charge of Ba is plus 2, therefore the subscript of Cl is 2. And then it will end up, Na will be displaced and will exist as your monoatomic element already. Alright, so take note that for a particular atom X, whichever atom it is in our compound, all the other elements before it in the activity series, or the more reactive elements than it, can displace that particular atom X. Meaning, aluminum can displace manganese, magnesium can displace manganese, calcium can displace manganese. Okay, or in terms of hydrogen, so in here, hydrogen can be displaced by lead, by tin, by nickel, by iron. All right, and all the other elements before hydrogen in the activity series. The same principle with fluorine or with the nonmetals. So fluorine can displace chlorine, can displace bromine, oxygen, iodine, and sulfur. All right. So for example, okay, copper sulfate and zinc. So the metals involved here, the ones that will be fighting out for the hand of sulfur or the sulfate ion, are copper and zinc. So the question is whether zinc will be able to displace copper, all right, and thereby forming zinc sulfate and copper. So take note that elements on the left side can displace elements on the right side. So if you have zinc, if you try to compare zinc, so zinc is here, and then copper is in here. Okay, so will zinc be able to displace copper? So take note that this is your reference element, copper. And since zinc is right before copper in the activity series, then therefore this reaction can happen. So zinc can displace copper, or zinc can substitute copper, okay? Or zinc can marry the sulfate ion and pull out or push away copper. Now, what if you have nickel and copper? So between nickel and copper, so uh, will copper be able to displace nickel? So take note that your Ni is your reference here. So and then you just have to look at whether for Ni to be displaced, then the free atom must be before Ni. Since you can see that Ni comes before copper, therefore nickel is more reactive than copper. So can copper displace nickel? No, alright? So this reaction cannot happen, so you expect no reaction to happen, alright? So in terms of the non-metals, the same principle. Elements on the left side can displace elements on the right side. So this is a battle now between bromine and iodine. So if you look at bromine is here and then iodine is here. So if your if your reference is bromine, you try to ask yourself whether bromine can displace iodine. Okay, and if it can displace iodine, then this reaction will be possible. So since you see that bromine comes before iodine, that means bromine is more reactive. Therefore, this chemical reaction can happen or is possible. However, if you have now iodine and bromine, so the other way around, can iodine displace bromine? Can the free atom I displace bromine? Okay, take note that bromine comes before iodine in the activity series. So this reaction is not possible. There will be no reaction. All right. So you just have to look at the placement of the free atom and the atom in the compound with each other. Okay, and find which among them is more reactive, which comes before the other. Now you try. If you can you predict the products of the following single replacement reaction? So let's say between zinc and HCl, okay, will zinc be able to displace hydrogen, okay, in the compound HCl? And then in the second example, will this is now between Cl and fluorine. So will fluorine be able to displace Cl? So non-metal to non-metal. In here, will aluminum be able to displace copper? All right. So in predicting, we just have to look at the activity series. So in here, zinc atom is our free atom. We are asking whether it can displace H. So for example, hydrogen is here, and then we see that zinc comes before hydrogen. Then we can say that yes, zinc can displace hydrogen. And so what will be our product? So we end up with ZnCl2 because the charge of zinc is Z plus 2 or 2 plus, okay? Zn plus 2. And then HCl, this is H plus 1 and Cl minus 1. So when you crisscross, so we are saying that the reaction is possible. When you crisscross, you get ZnCl sub 2. Okay, the sub 2 comes from the charge of zinc, which is plus 2. And then why is it not H only? Remember that monoatomic hydrogens are very reactive. So hydrogen in its elemental form should exist as a diatomic molecule. That's why you need to indicate that it is a diatomic molecule. It is H2. All right. In here, what will be our product? So, are we saying that fluorine will be able to displace Cl? So, based on this, yes, fluorine is stronger than Cl. So, we end up with NaF and Cl sub 2. So take note that the charge of sodium is plus 1 and the fluorine atom is minus 1. So when you crisscross, disregard the sign, that is NaF, and then chlorine cannot exist as a monoatomic species, so that's why it's a diatomic molecule, Cl2. In here, we have Al, Cu, and O3. So will aluminum be able to displace copper? So aluminum comes before copper in the activity series. So that means yes, it can. And our resulting product will be AlNO3 sub 3. Because take note that Al has a charge of plus 3, right? It belongs to group 3A in the periodic table. And then the nitrate ion, the NO3 group, has a charge of minus 1. So when you crisscross and disregard the sign, you end up with AlNO3 sub 3. And then copper will be a free atom. Okay, so it doesn't need to be diatomic because copper is a metal in itself. Alright, so that's it for predicting the products of single replacement reactions. Now we go to double displacement. So when you talk of double displacement reaction, it is just like exchanging partners. Alright, so exchange partners. So if in single replacement you have a third party, you have a kabit, then in double displacement, there is just an exchange of partners. So for example, between magnesium oxide and calcium sulfate, so take note that they have different reactivities and since they are paired with each other, so we expect a reaction to happen. So in here, the metal from compound A binds with the non-metal from compound B. So that's why you have uh, in here, magnesium pairs up with sulfur, calcium pairs up with oxygen. And then this will become your general formula. So AB plus CD will give you AD plus CB. So take note that A and your C are your metals and your B and D are your non-metals. So practically just an exchange of partners. And here are a few examples. So you have silver and the nitrate ion. So this is A, and then this is your B. All right, and then for example, the metal is denoted as C, and then this is D. So what we do have is an exchange of partners. It becomes A, then it binds with the non-metal of the other compound, AgCl. So this one becomes now AD, and then sodium C, and then B. Alright, so there is an exchange of partners. In here, potassium sulfate and barium nitrate gives you still the same exchange of partners, potassium nitrate and barium sulfate. And then how do we know, or how do we actually predict the different products? So take note, we just write their ionic forms. So potassium sulfate is coming from the reaction of K plus and SO4 2 minus. All right, and then barium nitrate barium has a charge of plus 2, and the nitrate ion has minus 1. And so once they exchange partners, it's like the FOIL method in math. Okay, insides, outside. Okay, first outside, inside last, if I remember it correctly. Okay, so potassium will react with the nitrate ion, so it ends up with KNO3. Okay, so crisscross, disregard the sign, you still have KNO sub 3. And then in here, barium and the sulfate ion, so barium 2 plus reacting with SO4 2 minus, you get Ba, supposedly Ba sub 2 SO4 sub 2, but we reduce it to its lowest terms, or to its least common multiple. So that's why you have BaSO4. Okay, and then the coefficients here just serve to balance the whole equation. So that's it for double displacement reaction. Now, let's practice predicting the products of the following. So HCl and AgNO3. So again, there is just an exchange of partners, but what is important here is that we know the charges of the compounds. So Ag, silver, has a charge of +1, the nitrate ion has a charge of -1. Uh, Hydrogen has a charge of +1, and chlorine has a charge of -1. And so therefore, if we exchange partners now, we end up with HNO3. So the metal pairs up with the non-metal, okay, and then we have AgCl. Now take note, chlorides are usually soluble except for those with mercury, with silver. So this one is an insoluble compound. So we say that this is a precipitate, okay? Or we denote the compound to be in a solid form. And the other compound is still aqueous, okay? So we are just working on general patterns, but what is actually happening can be found in actual experiments. But since we know that based on the types of based on precipitation reactions, chlorides having silver, mercury, and lead are insoluble, then we can deduce that this is a solid compound. All right. So in here, in the second example, calcium has a charge of +2 and chlorine has a charge of -1. Okay, just refer back to your periodic table. And then sodium has a charge of +1. The whole phosphate ion, okay, has a charge of 3 minus. So once we pair up the metal and the non-metal, then we can say that calcium pairs up with the phosphate ion with a negatively charged particle. So in here we can say that this is Ca and sub 3. Okay, the 3 comes the phosphate ion, and then we enclose the phosphate ion PO4 in a parenthesis, and the subscript there is 2 2 because calcium has a charge of +2. And the next compound, or the rest of the compounds, is NaCl. All right, NaCl. And then next, in the third example, so let's not be too strict yet with the subscripts. For the next example, we have PbNO3 and BaCl2. So from in the chemical formula, we can deduce that the charge of lead here is +2, and the nitrate ion is always -1. You can refer back to your polyatomic ion reference sheet, and then Ba +2, and then this is Cl minus. So what happens here is the metal bonds with the non-metal. So lead bonds with Cl. So since the charge of lead is 2 plus, then we can have the formula PbCl2. Alright? Since the charge of chlorine is -1. So if you crisscross, disregard the sign as PbCl2, and then this becomes, since the charge of barium is 2 plus and the nitrate ion is 1 minus, so we just crisscross, disregard the sign, BaNO3 sub 2. Alright? So you may pause this video and then, by the way, PbCl, just like AgCl, is a precipitate, so that is solid. Okay? So you may pause this video to absorb or reflect on the information and reflect on the process. And try to find out whether you can predict the products of the following reactions. Okay, so pause this video and on your notebook, you can give me the resulting compounds. Maybe we can skip first what kind of compound it is, whether it's aqueous, gas, or liquid. So just follow the pairing up or predict the product. Okay, on your own now. So here are the following answers with the thought processes involved. So first is we have to identify the charge for each particular atom. So in here, since we see that it is FeCl3 and not as FeCl2, then the charge of iron in this fourth example is +3. Okay, so that when it reacts with the hydroxide ion, which has a charge of -1, then we get iron FeOH sub 3. And take note, this is one of the insoluble compounds, the hydroxide of a metal. So we write the downward arrow to denote that this will be our precipitate. And the rest is Na reacting with Cl. So Na plus Cl minus, that's NaCl. In here, hydrogen has a charge of +1, and in the sulfate ion, from the subscript here 2, so we know that it is 2 minus. So if they react with the hydroxide ion, you have H plus OH minus, you get HOH, right? Which can be reduced into H2O, liquid. So this is our liquid, and then Na plus reacting with the sulfate ion, you get Na2SO4. Okay, in here you have K plus and OH minus. So copper pairs up with the hydroxide ion, which is negatively charged. So that's why you have copper hydroxide, copper 2 hydroxide, CuOH sub 2, and potassium sulfate, K plus, reacting with the sulfate ion, K2SO4. Alright, so take time to absorb and reflect on the answers. The last type is actually combustion reactions, the last type of classification. So when you say combustion reactions, it's usually a reaction between a hydrocarbon with oxygen gas. So there are three requirements. The first one is that there must be fuel, and then there must be oxygen, okay, and there must be an activating agent, which gives the reactants enough energy for them to be able to break and form new bonds. Okay, and combustion actually refers to burning. All right, so you have here a fire triangle. So you have heat or energy, activation energy, the fuel, and oxygen. That's why if you've noticed, whenever there is a fire, the goal is to really limit the supply of oxygen present. So if you have some fire on your lap gown, you roll over, or you have your mat, the fire extinguishing mat. Okay, so that's it for combustion reactions. So the products are carbon dioxide and water. Okay, and you have the following general form. So it can be any hydrocarbon. So when you say hydrocarbon, these are made up of carbon and hydrogen, and it reacts with oxygen to form carbon dioxide and water and release energy. Okay, sometimes if the reaction is incomplete, then you will be able to see carbon monoxide, the black product or soot. Okay, that's CO. If there is any one of these reactants that are limited, or limited, so as to have an incomplete combustion. Okay, now combustion is used to heat homes and run automobiles, such as octane in gasoline, that's C8H18. Here are a few examples of hydrocarbons with their corresponding equation. Okay, and then in here it gives us the amount of heat that is released. Okay, so if you notice, the more negative it is, the more energy will be released in here. All right, so those are for combustion reactions. So again, there are 5 types of reactions: synthesis, analysis, single displacement, and double displacement, and combustion reactions. Okay, I'd like you to pause this video and try to identify the type of chemical reaction, okay, as a way of practice. And here is the answer key. Okay, so DD represents double displacement, SD represents single displacement. So you have decomposition, combustion, and composition. I hope you got them all correctly. All right. So because if you identify the types, you can readily identify the pattern and therefore predict the products of chemical reactions based on the type. All right. So that's it for this lesson. So we were able to distinguish the types of chemical reactions and predict the products of chemical reactions. So stay tuned for more lessons on chemical reactions and stoichiometry.